Good morning, everyone. If you find yourself on the European continent, or good afternoon, evening, if you find yourself farther east in the Asia Pacific area, I'm really excited to give you this presentation today. And the goal really will be to talk about some of the strategies and processes for multi-instrument harmonization as we continue this second part in this cell therapy production series around QC and IPC. So the first webinar in the series was focused on automated sample acquisition and analysis of cellular products using our Express Mode software tools. Again, we'll have today's discussion, and then in approximately 2.5 weeks, we'll have another presentation on July 9th and July 11th, focusing on the reagent aspect. And so today we'll talk about multi-instrument harmonization, some of the strategies that are in place for that now, and also some of the tools that we offer at Miltenyi Biotec. So as a rough agenda, we'll have an introduction, but also a short recap of the first webinar. We'll talk about the harmonization of instrument performance and some of the steps that are required there. And then we'll look at the multi-instrument harmonization with smart gains, and finally a summary as we finish. So in review, CAR T-cell manufacturing is a complex process. It starts with the sample preparation and goes through a various array of different selections, expansions, activations, transduction, and then of course the final product formulation. During that time, it's necessary to run different IPC and QC steps to ensure the consistency, reproducibility, and that the product is progressing to the expected time point. One thing I've noticed that over the last years, the reproducibility of the manufacturing has really improved. And so as a global product manager, when we have some of the large companies coming in to visit us that are running these CAR T therapies and considering future options, they're starting to talk more about the bottleneck that's coming up from this IPC QC step and the need to get the products out faster, QC'd quicker, and even more importantly, the reliability, consistency, reproducibility, and measurement assurance that's required for this type of work. And so when it comes to IPC, QC, there's different areas that include multi-parameter analysis, also things like qPCR, and then maybe the most important area, the safety testing for microbiome, for endotoxins and mycoplasma. The focus of our discussions today and through this webinar series are really around the flow cytometry aspect for analyzing cellular composition, viability, counting, also looking at the transduction efficiency, how well is our CAR expressed in our samples, potential potency assays that could arise in flow, and then what kind of cell impurities might exist in our samples. This was a figure that was presented in the first webinar, but it talks about the irreproducibility of data globally. And this is related to a research article that was published in PLOS Biology. I would like to think that in the context of manufacturing and these spaces, that we don't have some of the same reproducibility challenges that are expressed so highly here with this 28 billion figure that's described. But we still have the challenges of reagent reproducibility, ensuring data analysis and reporting consistently, that the study design or the experimental design for the QC is as robust as it could possibly be. And then in the case of multi-instruments or multi-site manufacturing, that the protocols that are delivered from site to site are reproducible by each site, and that they also give you consistency. The first webinar, again, was focused on the Express Mode aspect of this. And one key component to the Express Mode, of course, is the instrumentation. So there was a short introduction to the Max Quant Analyzer 10 instrument for IPC-QC. This device delivers automation for things like startup, shutdown, cleaning, sample labeling and processing, calibration QC, volumetric counting, and then, of course, the Express Modes for automated analysis. It also delivers the simplicity for ease of use, so low demand for experience if you have people that are less familiar with flow cytometry. And then it's really focused on consistency. So unibody optical bench that's manufactured out of milled metal, um, and of course the ability to perform multi-instrument alignment, which we'll discuss today. And then from the control standpoint, having 21 CFR Part 11 packages for the software, tools like live remote support, and then system logging are all things that aid in this area. So the express modes, what are they? They're an algorithm-based data analysis method. They're highly application dependent, so we customize these and optimize them for particular focuses, which is really why they're so well suited for a manufacturing setting where you are going to be analyzing the same cell populations over time, and where you do want a lot of reproducibility and consistency. And so these express modes are based on a significant amount of data that's acquired. And unlike snap gating, express modes use population statistics and logic for the gating process and not just central tendencies only. The express modes really achieve, and the goal of them is to reduce human error from gating between users or between sites, to decrease the data variation, which in the end is going to give you more accurate results, of course, to deliver the reproducibility, and to provide a really simplified workflow for the operator, and in the end increase productivity, but also measurement assurance. An example of an express mode is shown here with our CAR-T transduction process. And so what this looks like is we have in our gating strategy our scatter for our cells, CD45 positive, our CAR versus our viability dye, in this case 7AAD, to get viability of our product, the CD3 population, and then the transduction efficiency of that CD3 population. We also have some other markers in there for subset analysis like CD4 and CD8 T cells. So that was the review. Now we're going to focus on the multi-instrument harmonization piece. So in this video that just flashed before you, you get the idea that something's being delivered out from these central instruments from multiple sites around the world. So one of the topics and challenges we want to talk about and review is the challenge to get reproducible data from one site to another, or even within the same lab when you have a case with multiple instruments being there. So how do you achieve data harmonization, and is it possible to have data harmonization without instrument harmonization? So the express modes bring this next level approach for automated analysis and reproducibility, but is it the only consideration? I would say no. What's necessary? To deliver that reproducibility, you really have to have assurance in intra-instrument and also inter-instrument. So let's take a look at some of the considerations to achieve multi-instrument harmonization. When you look at in a stepwise approach, assay design is the first thing you'll tackle. Of course, that's important. You'll also need to consider differences in hardware and design, depending on how your study or your goal, and if you have different instruments from different vendors. You'll need to ensure performance over time. You'll need a process to calibrate from device to device, and then you need to address kind of transporting key pieces of information and knowledge from one site to another. So let's focus and look at the first aspect of this. When it comes to panel design and assay design, of course, you want to look at from a biological perspective, how can we reduce the amount of spillover and spreading from the fluorochromes and the reagents that are used. So just an example of some of the dyes we offer at Miltenyi are listed down here. You also need to consider designing a panel that could be compatible with multiple instruments. So what are common laser lines that are used and common fluorochromes that can be analyzed and run on multiple instruments. And then you need to also start to think about what kind of control materials will be available to you, whether it's commercially available controls. Maybe you generate a master cell bank of your cellular material, and maybe you do a combination of those things to ensure that you can validate and run these assays for your particular application in cell manufacturing. The next consideration is around hardware and design. So you have optical components such as the lasers. Are their wavelengths and power the same from device to device? What type of filter and mirrors are used in the optical path as the light is going to each detector? We need to think about what detection components are there in general, whether it be PMTs, photodiodes, or something like an APD. We need to consider our data display. So Are there differing fluorescence values coming from one device to another? And then we need to think about, again, in the end, is there data reproducibility intra and inter-instrument possible? One of the studies that was done a few years back by the National Institute of Standard and Technology and ISAC was around cross-calibration of instruments using hard-dyed beads. These are a great reference material. Some of the devices that were run were listed here, including 17 Max Quants. When we look at the data from the different vendors, so these are different calibration products from different vendors, FlowSet, CS&T, rainbow beads from Serotech, and then a thermo product with this cytocal beads. You'll notice where I've highlighted here, there's nice tight CV. So it didn't only tell us what kind of quality came from each of these vendor beads, but it also told us a lot about the instruments that were in the study themselves. And so you can see kind of the reproducibility and consistency that's available in our MaxQuant optical benches. Next consideration is ensuring performance over time. So once you've identified, of course, your assay and you've worked out those logistical details, you need to identify how you're going to control your method. There's several ways to do this. One way would be to use single stain beads as a MFI marker and gate on those and ensure that that fluorescence intensity is maintained throughout your study from day to day. Or you can use something like a rainbow particle. Checking that the target MFIs are met, and then adjusting the gains as required is really the next step in that process once you have identified the product that you want to use. The data down here is an example of a multi-peak bead that was used in a study to ensure that if we kept the gains constant throughout, that the MFIs that were recorded were consistent over time, and you can see kind of how that broke out over a number of different channels. The paper is mentioned here at the bottom. For calibration, this is maybe the key translational aspect. So once you've identified the key pieces here of information mentioned before, you need to be able to translate that from device to device. One of the challenges or the things that makes this tough is that there are intrinsic differences of each detector on each channel on each device that need to be independently optimized. And that's just inherent with the design of some of these detectors. They don't require the same voltage to receive the same fluorescence values on the back end. The good thing is they behave linearly and they can be calibrated to each other. Another key component of this calibration is the reagent staining and harmonization. That really needs to be ensured as well, that you're not delivering any kind of additional variability there, which might affect the quality of the data on the back end. And after optimization, you need to always monitor and ensure and adjust manually any changes in the gains that would be needed to achieve the same target fluorescence values. And so what does this look like? You start with a master device for your optimization and validation. So establish your optimized settings on your master device for your assay. You then are going to record or reference a control material. We mentioned this a few steps earlier, such as single floor beads or another control material that has a known MFI target in them. And then you optimize your additional devices using the control material to achieve that same target MFI from your master device. What does this look like on multiple instruments? Again, pulling from this paper, there is an overview of some of the gains from many different devices at many different locations. So device A was a single vendor device, but across 3 different sites. So you can see 11 different centers participated. And you'll notice that the ranges of the gains that were used to achieve this performance of harmonized instrument settings were quite different. I've given a delta at the bottom just to give you an idea on each channel how much that range looks like. So up to 203 gain steps were required to achieve the same performance on some of these devices. And this is where I think a lot of the harmonization challenge comes in, and the, let's say, a barrier for translating it from device to device, and then the need to monitor it over time. So to summarize that process in 4 steps, you're identifying your settings and validating them on a master device. You're optimizing the settings on an additional instrument to deliver the equivalent MFIs. And then long term, you need to monitor the gains in performance, make adjustments as necessary, and then ultimately ensure that the harmonization is happening over time. The last piece is managing the complexity, and I kind of was hinting at that all along. The knowledge of your staff at your locations, the reproducibility of the optimization and setup, and sometimes geographical proximity all make this a more complex process. So arguably you have highly skilled at your central site that did the master device setup, but do you also have the same level of knowledge in your satellite sites? Can you count on that and guarantee it? You need to also consider that and also have a strategy in place to make sure that you reduce any barriers for your satellite sites so that you can achieve equivalent performance globally. Now, we'll kind of introduce the smart gain technology and what that brings for this global cooperation standpoint. So it's really around consistency you can count on from test to test within one instrument, from user to user, from instrument to instrument, and across your sites. So whether you have multiple instruments in one location or sites around the world, this smart gain technology is really aimed at delivering consistency and reproducibility. And so I think the question is, what makes that possible? The calibration and beads ensure consistent results. And so this Lighthouse is used as kind of a representation of a stable, bright point that can be calibrated against using calibration beads. And so inside our calibration beads, we have known fluorescence values that should reach a specific median intensity. We have a device A shown here. It requires to get to 600 a gain of 400. So after each daily calibration in QC on the device, the Max Quantify software on the instrument automatically adjusts the PMT gains to ensure that consistency. This is possible because the instruments, again, are calibrated to this known fluorescence value. In the case that we have a second device, device B here, it might require 430 volts or gain steps to get to that same brightness level. And this is what we saw in the data from the previous paper I showed earlier, that there was different requirements across sites. What we've done with smart gains is we've harmonized this so that every instrument, no matter where geographically it's located, can achieve the same performance with those instrument settings. So you get consistent results with the simplicity of a universal instrument setting. We'll look a little closer at what this means and how it's practically delivered on each device. So let's take the example of instrument A as our master device. We optimize our instrument settings there. The next step is to save that instrument setting file. And the third piece is just simply transferring that instrument setting file to the next instrument or instruments. All of the key information that's required for this calibration process in smart gains is inside that instrument setting file. And so from a user perspective, all you have to do is save the data from one device, load it onto the second device, and continue on with your assay. And so earlier we talked about this strategy, and you might remember this slide, of identifying the settings and validating them, and then having to go through the optimization process on other instruments, and then the need to really monitor and ensure that performance over a long period of time. What this looks like in context of smart gains is, of course, you still will need to go through the identification, validation process, but then you'll simply load the instrument setting on the additional device. After assay optimization and validation, it's a simple transfer. So smart gain technology really manages that harmonization natively. What does this look like on multiple Max Quant instruments? So as you can see here, all of these devices had the same gain values listed for each channel that was used. And again, this is one of the benefits of smart gain. It allows the harmonization of your devices from instrument to instrument to ensure performance over time. So there was no difference in the reported gains here. So with this, we get that harmonization natively without having to go through the hoops and jumps to get there of optimization with these multi-cal beads, for example. So not to give credit where it's due, we talked about the two steps to get to that point. It's still important that you monitor performance and ensure harmonization over time, but you shouldn't have to go through and manually make the adjustments this will be done for you automatically and for your sites. So when it comes to an evaluation question, I think data is always, the proof is in the pudding. And so we'll take a look at a study that was done here, which we've been referencing throughout, where they conducted this MFI strategy. When you look at each of the populations listed here, these are cell populations and their frequency based on percent gated. And you'll notice the CVs range anywhere from 2% on up to 23% in some cases. It really depends on how rare the population is. But this again they followed this strategy, they achieved multi-instrument harmonization. This is the kind of variability you might expect from device to device. We wanted to kind of reproduce a similar study back here at our headquarters in Bergisch Gladbach. So we used our 8-color immunophenotyping kit to do that. It's a product that's commercially available from Miltenyi. Here's some of the markers and the gating strategy that's listed. So we have, of course, scatter, CD45 gating, and then looking at the subsets. So T cells, monocytes, monocyte subsets, B cells, NK cells, and NKT cells are listed down here, neutrophils, and then your T cell subsets for CD4 and CD8. So the experimental design or plan that we had was we had 5 instruments on our campus here. We used the 8-color immunophenotyping kit with a stained lysed whole blood product. From there, we did data acquisition using our express modes that were mentioned earlier, so the full automated acquisition and analysis of each population, so there was no input from the user for gating, etc., for the numbers we're going to see in the next slide. And we used 3 members of our marketing team, kind of not to say that we don't have a scientific background, but we're definitely not running flow data every day. So this is just to show the simplicity from non-experts. The short protocol overview, we stained the master control, so 1 sample, 1 donor was used throughout this study, and the settings were developed and optimized on a single device. So we made the settings on 1 instrument and pushed them out to all the other devices, to the 4 additional ones in the study. On each instrument, 3 measurements were taken. And the data that's shown here was what we got from a reproducibility standpoint. Again, this is population frequency for B cells, eosinophils, neutrophils, T cells and T cell subsets, NKT and NK cell subsets. Our donor in this case had very few intermediate non-classical monocytes, so the CVs were high here, but when there's really such a low event rate or event count for a population, we would have needed to acquire a lot more data to have statistical significance, so we would expect to see the high CVs in this case. When we look at the fluorescent histograms for the neutrophil gate, on the master instrument, we have the 3 measurements overlaid here, and then all the other subsequent instruments, the 3 measurements that were taken on each device. And this is just to give you an idea of the reproducibility of the instrument setting for the same donor on multiple instruments. And then finally, the overlay of all of the samples that were run in this final graph. So in summary, the goal is really improving reproducibility, quality, and robustness is going to require the harmonization of your SOP and design, the instrumentation, the analysis process, and of course the reagents that are used. So the instrumentation and analytical packages can be a key aspect of delivering reproducibility, quality, and robustness. These are things that we feel like we offer with the express modes and the MaxQuant analyzers that were discussed in the first webinar. The device-to-device harmonization is made possible through validation, so that's the key upfront piece, but it can be ensured and made simpler with automation. And so, of course, follow the guidelines that are there from the ICH and the Pharmacopoeia as it relates to method validation, but using something like a tool like SmartGains to help with the alignment piece is something that we believe is a step forward into the next generation of multi-instrument harmonization. All right, so we got a question on how are the PMT gains ensured in the SmartGain and given uniformity across the site. So again, it really comes back to the calibration process. and that the beads that we use, because they're hard dyed beads, they're very stable. It really honestly any temperature and over any period of time. So we've seen great stability over the last years in the calibration products we offer because they're polystyrene hard dyed beads. From there, that's what delivers the consistency of the instrument settings. We're able to calibrate to those beads every time the instrument's turned on and calibrated, and that's translated into the gains that are there. So the gains are linearized by a kind of proprietary process we use, but from a practical standpoint, the operation is no different. The gains are not critical in the sense that up until this point, there was no way to have multi-instrument harmonization without individually optimizing each gain. We've just categorized the performance of each of the PMTs so that we know the set gain values, and we can deliver a scaling that makes it a lot more easy for our users to operate. Another question that just came in was, is the Smart Gain available on all of our MaxQuant devices? Yes, so the answer is yes. The main requirement for that is that the devices have the software package 2.13, and that will include the Smart Gain technology. All right, so thanks for your questions. I'll also go ahead and introduce the next webinar. So on July 9th and 11th, if you're available, we'd love to have you join us again. We'll talk about reproducible flow cytometry data with lot-to-lot consistency using our recombinant antibodies and reagents. And so in the follow-up, we will, if you registered for this event, you're obviously receiving our emails. We'll send an email with the link. You can also, as soon as it's live, register for the next event. So, and then again, it will cover when quality matters in flow cytometry reagents. We'll talk about some of the tools we have available and the design of these reagents to ensure reproducibility. All right, thank you everyone for attending. If there's no more questions, we'll go ahead and sign off. Wherever you are in the world, we wish you a wonderful day or a wonderful evening. Thank you again for joining us. If you have any questions, feel free to contact us directly